Good morning, everybody. Today, the topic for discussion is quantum mechanics. Let's have a brief look on the outline. So, we are going to discuss about the introduction to quantum mechanics, black body radiation, and Planck's law, photoelectric effect, Compton effect, de Broglie hypothesis, which is wave particle duality, Davidson and Germer experiment, Heisenberg uncertainty principle. Bond's interpretation of the wave function, which is nothing but physical significance of wave functions stored in the time-independent wave equation and the application of it, which is a particle in one-dimensional box in our case. Next, coming to the basically the introduction, quantum mechanics is a new branch of study in physics, which is indispensable. It means it is very important to understand the mechanics of particles in the atomic and subatomic scale. The motion of macroparticles can be observed either directly or through microscope. Classical mechanics can be explained to explain their motion. We call it as Newtonian mechanics because it follows the Newton laws. But classical mechanics fail to explain the motion of microparticles like electrons, protons, and this black body radiation, Compton effect, photoelectric effect, etc. Max Planck is a scientist who proposed the quantum theory to explain black body radiation, and Einstein applied it to explain the photoelectric effect and all, etc. What is a black body? Before going to the concept of black body radiation explanation, what is a black body? It is a body which absorbs all wavelengths of radiation incident on it when it is at low temperature, or it emits different kinds of wavelengths of radiation at high temperature. That means when we heat it. So that kind of body we call it as black body. For example, lamp black. Okay. Now, here if you observe the radiation emission of a radiation spectra for a black body, this is how the spectra will be. Here, emitted energy as a function of wavelength of the emitted radiation, it was drawn plotted. The temperature of the body is raised to different values and distribution curves are plotted for different values. Here if you observe for 1100 Kelvin, 1300 Kelvin, 1500 Kelvin and 1700 Kelvin. So in order to explain this black body radiation, like several scientists tried, and one of that is Stefan Boltzmann law, in which the emitted energy is directly proportional to the fourth power of temperature. You could able to explain with this formula, and here sigma is the proportionality constant, okay, and T is the absolute temperature, but it could not able to explain throughout the region of lambda at from lower wavelength to the higher wavelength. Next, for the radiation power, m lambda of T, it is a function of lambda for a constant T, and it's a Wien's displacement law where lambda T equals to B. Here, lambda is put at the peak, that peak position, the value of lambda, lambda max we call it as, and lambda T equals to constant. That's what they observe. And Wien's law is energy emitted is directly proportional to T power 5, or it equals to constant into T power 5. Wien's law is valid at lower wavelength region, whereas it deviates from experimental values at higher wavelength region. That means it could not able to explain throughout the spectra from lower to higher wavelength region. Rayleigh's law, another scientist, they try to explain with the principle of equipartition of energy, U lambda d lambda equals to 8 by kb t power minus 4 d lambda. Here kb is the Boltzmann constant, and this is Rayleigh's equation. This now correctly predicts the fall of intensity in the longer wavelength side. However, it fails to explain the lower wavelength side of the spectrum. So finally, in order to explain this black body radiation, there are like two to three different sets to explain it at shorter wavelength and at higher wavelength. But nobody could not able to give a proper explanation throughout the wavelength region. So at this stage, Planck's law, Planck he assumed that he has given a good explanation for this black body radiation. He assumed that the walls of the black body consists of a large number of electrical oscillators vibrating with their own natural oscillator, possesses an energy equal to h nu, where h is the Planck constant and nu is the frequency of the oscillator. An oscillator may lose or gain energy by emitting or by absorbing photons respectively. Planck derived an equation for the, so there are like some postulates of to be followed in this Planck's law. Planck derived an equation for the energy per unit volume of black body in the entire spectrum of black body radiation, and is given by E lambda d lambda equals to 8 pi hc by lambda power 5 into 1 by e power h nu by kBt minus 1 d lambda. So by applying the postulates, Planck's postulates, we could able to derive this equation for emitted radiation, which followed throughout the wavelength region well. Next, photoelectric effect. What is a photoelectric effect? Photoelectric effect is nothing but when the radiation incidents on any metal plate, particularly, uh, the incident radiation will be absorbed by the electrons which are on the surface of the metal plate, and they will acquire high energy. They excite and acquire energy and detach it from the plate surface and starts moving, which we call it as movement of electrons. We call it as current, and the current contributing from this photo emission, we call it as photoelectric current, and the electrons which are traveling we are calling as photoelectric electrons. Here in this case, actually it is inconsistency with the classical light theory. According to the classical wave theory, maximum kinetic energy of the photoelectron is only dependent on the incident intensity of the light, but not on the light frequency. However, experimental results show that the kinetic energy of the photoelectron is dependent on light frequency. So, in order to explain this, Einstein used the Planck radiation law and the concept of energy quanta. He introduced the photoelectric experiment. Energy quanta is nothing but energy. It is not in the form of continuous fashion. It releases in the form of small quantities, which we call it as energy packets or quanta. Photoelectric experiment results suggest that the energy in light wave is contained in discrete energy packets, which are called energy quanta or photon. The wave behaves like particles. The particle is photon. Planck's constant H equals to 6.625 to 10 power minus 35 joule second. Photon energy H nu, work function of the metal material, that equals to H nu naught. Here work function means it is the minimum amount of energy required to eject the electrons from the metal plate surface. That much energy is we call it as work function. And maximum kinetic energy of a photoelectron Tmax after releasing from the surface, the maximum energy we can obtain is H into mu minus mu naught. Planck-Einstein energy quantization law and photoelectric effect. For this photoelectric effect, Einstein used relations H nu equals to W plus half mv square. Here W represents the work function and half mv square, which represents the kinetic energy of electrons which are ejected. Okay, here he reduced it from E is equal to H nu. Here nu is nothing but C by lambda, H C by lambda, and E equals to MC square. We know that. So with the using of the two relations, we could able to get the final equation H nu equals W plus half mv square. This is the Einstein equation for photoelectric effect. Next, another important task is Compton effect, a phenomenon called Compton scattering. It is observed by Compton in 1924, provides additional direct confirmation of quantum nature of electromagnetic radiation. Okay, this is the experimental arrangement to prove this. X-ray impinges on matter. Some of the radiation is scattered, just as the visible light falling on a rough surface undergoes diffuse reflection. Scattered radiation has smaller. So the scattered radiation has smaller frequency, and of course, smaller frequency means longer wavelength than the incident radiation. The wavelength of scattered radiation depends on the scattered angle phi. Now, explanation based on the classical principle, scattered mechanism is induced by motion of electrons in the material caused by the incident radiation. This motion must have the same frequency as that of incident wave because of forced vibration. And so the scattered wave radiated by the oscillating charges should have the same frequency. There is no way that the frequency can be shifted by this mechanism. But in practical, if we observe what is happening, the scattered wavelength, the scattered beam is having two wavelengths. One is unmodified. The other one is having lesser, it is having lesser energy. That means longer wavelength. The quantum theory, by contrast, provides a beautiful, simple explanation. We imagine the scattering process as a collision of two particles. Here it is a elastic collision. Elastic collision means it follows the conservation of energy and conservation of momentum. The incident photon and then this elastic collision is between the two particles. One is incident photon and an electron which is at rest as shown in the figure. Here I show you this is how. The photon gives up some of its energy and momentum to the electron, which recoils as a result of its impact. And the final photon has less energy, smaller frequency, and longer wavelength than the initial one. Theoretical derivation. Suppose that lambda naught and lambda are the wavelength of the incident and scattered radiation respectively. The Compton effect could be described by the following procedures. First one, using relativistic theory, energy conservation, and momentum conservation. Okay, by by applying the energy conservation before and after the collision, and by applying the momentum conservation before and after the collision, by equating these equations, we can get the final equation for quantum shift. Let's see. The key points of derivation for this procedure is relativistic theory is equal to h nu, where E square here equals to C p square plus m naught C square. Uh, when m naught is equal to 0, the momentum is equal to P equals to E by C, h nu by C, h by lambda, direct we know this. And energy conservation, h nu naught plus m naught C square. H nu naught is the energy of incident photon. M naught C square is the energy for the electron which is at rest is equal h nu plus m C square. H nu here is the photon energy and m C square recoil electron energy. So h by lambda naught plus m naught C, all sides I am taking out, cancelling it out the C and replacing mu with C by lambda. For electron, we have E square is equal to C square plus m naught C square. That's for energy term. And mv square is equal to mv square minus m simplification of this one. And momentum conservation, that means momentum before collision equals to momentum after collision. For this, we need to take the combinations. Before collision, the momentum of electron is 0, hence left hand side only one term come momentum for the photon, and the right hand side momentum for the photon along with the momentum for the recoil electron. Okay, by simplifying all these equations, the final form will be lambda minus lambda naught, which is we call it as 2 here h by m naught c 1 minus cos phi 1 minus cos 2 theta. We can write it as 2 sin square theta. 2h by m naught c, by using the mathematical relations, we can get 2 lambda c sin square theta by phi by 2. Here lambda c is the Compton shift, which is h by mc, that equals 0.00243 for phi is equal pi by 2 value. And next concept is de Broglie hypothesis. The real nature of light possessing both wave and particle properties was explained by combining Planck's expression for the energy of a photon equals to h nu with Einstein's mass energy relation E is equal to mc square, where c is the velocity of light, h Planck's constant, and mass of the particle. So here we are applying both. We are considering both the natures like wave nature and particle nature. H nu equals to mc square. I am like equating it, introducing mu equals to c by lambda. We know that we get hc by lambda is equal to mc square, or lambda is equal to h by mc, which is h by p. Mc is nothing but momentum. H by p is the momentum of the particle. Lambda is the de Broglie wavelength associated with the photon. Okay, as lambda is equal to h by mv, h by p. The above equation represents the de Broglie wave equation. Now, wave particle duality, particle like wave behavior, it is an example for it is photoelectric effect. Okay, and wave like particle behavior, it is an example for it is Davidson-Germer experiment. Now, wave particle duality, mathematical description for it is the momentum of a photon, I can represent it as equals to h by lambda, and whereas the wavelength of a particle is lambda is equal to h by p. Lambda is called the de Broglie wavelength. Davidson and experiment, if this is proof for wave nature of a particle. Okay, Davidson and Germer experiment. If you see, uh, so So if you observe here, the experimental arrange here, electron beams are collimated to form to fall on crystal, nickel crystal here we have taken, and after that they will be scattered and collected in a Brock spectrometer. Here, if you observe the mechanism, the electron beam is accelerated and made to strike on the nickel crystal, and a short maximum is occurred at an angle of 50 degrees with the incident beam. The incident beam and the diffracted beam in this experiment make an angle of 65 degrees with the family of Brock's plane. And here the accelerated electrons are moving with potential 54 volts. Actually, we are considering the electrons as a wave. So we can use it for the calculation of D, that interatomic space, D equals to 0.091 nanometer. According to Bragg's law for maxima in diffraction pattern, 2D sine theta equals to n lambda here. N is equal to 1 and lambda equals to 2D sine theta. By substituting these values, we can get 0.165. This is from experimentally. And for a 54 volt electron, the de Broglie wavelength associated with the electron is given by 12.25 by root V. We will get 0.166 nanometer. This value is good agreement with the experimental as well as theoretical values are both are coinciding. This experiment provides a direct verification of de Broglie hypothesis of wave nature of moving particles. Now, the duality of light, of course, the concept that waves carrying energy may have a corpuscular aspect and that particles may have a wave aspect. Which of the two models is more appropriate will depend on the properties the model is seeking to explain. For example, waves of electromagnetic radiation need to be visualized as particles called photons to explain the photoelectric effect. Now you may get confused that two properties of light and ask what is the light actually is. So in order to overcome the uncertainty principle, it is impossible, it describes that it is impossible to simultaneously calculate the accuracy of the in position as well as momentum of a particle at a time. That means delta p into delta x is greater than or equals to h by 2 pi or some constant. Okay, here delta p is the uh, like error in calculating the momentum. Okay, and it is impossible in the same way. uh, the other two parameters, the pair of the another parameter set is energy and time. So the Heisenberg uncertainty principle applies to electrons and states that we cannot determine the exact position of an electron. Instead, we could determine the probability of finding an electron at a particular position. Next, Born's interpretation of the wave function or physical significance of the wave function. So here Max Born in 1926 gave a satisfactory interpretation of the wave function psi associated with a moving particle, postulated that the square of the magnitude of the wave function represents the probability density of the uh, wave function and psi is the probability amplitude. Thus, the probability of the particle within an element volume d tau will be psi square d tau. Since the particle is certainly somewhere, the probability will be 1. A wave function that obeys the above equation is said to be normalized. So the three conditions, the three limitations are it must be finite everywhere, it must be single valued, it must be continuous and have a continuous first derivative everywhere. Now, Schrodinger's time-independent wave equation. In one-dimensional, the time-independent wave equation is minus h per square by 2m d square psi by dx square vx psi x is equal to E psi. Here, V is the potential, E is the total energy of the electron we consider. In three dimensions, the same equation will be minus h per square by 2m del square psi r psi of r plus V of r psi of r equal to E psi of r. And the application of Schrodinger time independent equation is particle in one dimension box. Here particle means electron. Okay, and the dimension box is nothing but it is a unit cell in a crystal. That unit cell we represent it as crystal lattice, we represent it as the one dimension box. Here particle in potential well of finite height v equals 0, where within the limits the unit cell limitations 0 to L, within that range the potential is zero, and at the walls of the cell and outside the cell, the potential is infinite. The Schrodinger one-dimensional time-independent equation we know for freely moving particle V equals to zero, and taking 2me by h per square as k square, some constant, considering it, equation 1 becomes dou square psi by dou s square plus k square psi is equal to 0. Now, equation 1 is similar to the equation of harmonic, simple harmonic motion, and the solution of above equation I can represent it as a sin kx plus b cos kx, where a, b, and k are unknown quantities, and to calculate them, it is necessary to construct boundary conditions. Hence, boundary conditions are, we know the boundary conditions at the x is equal 0, psi is equal 0. Okay, and when x is equal to psi is equal to 0. By applying that, when x is equal to 0, psi is equal to 0, which gives b equals to constant b equals to 0. And now I am applying the second boundary condition at x is equal to 10, psi is equal to 0. Now a sin kl plus b cos kl. Already b is 0, so a sin kl is not going to be, you cannot equate it to 0. So surely sin kl will be 0. Now kl equals to some n pi. Okay. Now k is equal to, because sin n pi is equal to 0. K is equal to n pi by L, substituting the value of K in equation 3, 2mg by h square is equal to K square, we know there. So n square pi square by L square. Now by simplifying this, we can get the equation for E equals to n square h square by 8mL square. In general, En is equal to n square h square by 8mL square. L is the length of the unit cell. Okay. The wave equation, the wave equation can be written as sin is equal. Now we are going to write down the wave equation. Psi is equal to a sin n pi x by a. Let us find the value of a if an electron is definitely present inside the box. Then from the normalization condition, minus infinity to infinity, psi square dx equals to 1. Here I am keeping the psi square. It will be 0 to L sin square n pi x by L dx is equal 1 by a square. So by simplifying this, a is equal to 2 by L. Psi n equals to root 2 by a sin n pi x by L. Now this equation 9 represents an energy level for each value of n. The wave function is given in equation. Therefore, the particle in the box can have discrete values of energies. These values are quantized. Let's see how we can represent it. So, particle in an infinite potential well, 4 lowest discrete energy level, n is equal to 1, 2, 3, 4. Further, the corresponding wave function will be that B it is showing. That is how the wave motion will be, and corresponding probability functions are, this is how we can represent. Okay, and thank you. This is a brief introduction of quantum mechanics.